Friends, very good morning to everyone. We are dealing with the synthetic strategies for peptide synthesis. We know that it can be effectively synthesized both by solution phase method and by solid phase method. In both the methods, we use either convergent strategy or sequential strategy. Any of the methods we use, it has some problems. Today's subject of discussion is the problems faced during the synthesis of peptides. The possible problem, one of these is aggregation. What is this aggregation? Peptide chain has the tendency to form secondary structures. These secondary structures which is formed is also called as aggregates, and that's why the process as aggregation. This aggregation occurs either with the peptide chain or with the polymeric support. The cause for aggregation is either hydrogen bonding or hydrophobic interactions. This aggregation generally occurs when the peptide has high content of alanine, isoleucine, asparagine, or glutamine. Another possible problem during the peptide synthesis is enantiomerization. During the coupling reaction, we activate the carboxy group. When we activate the carboxy group, it activates the acidity of hydrogen atom present on the alpha carbon. Thus, this leads to a interaction and give rise to the enantiomer, which is inactive, which is of no use for us. This enantiomerization occurs when there is cysteine or histidine or proline or methionine or tryptophan or any hydroxymethyl containing based resins. When these amino acids are present and which is connected to hydroxymethyl based resins, then possibility of enantiomerization is there. Another problem is the side reactions. We know that the side reactions are generally lesser provided we protect the amino acid properly and follow the correct procedure. Aspartamide formation can occur if aspartic acid is coupled with either glycine, serine, asparagine, threonine or arginine. And let us look into the side reactions and how to overcome that. Why this side reaction should occur? This is because of the fact that all the amino acid has the basic skeleton rings similar, but it has various different side chains. The functional groups present on this side chain may be either acidic or basic or neutral. And this type of functional group present are prone for side reaction during the peptide synthesis. Why is this so? It is due to the interaction of these functional groups present on the side chain with the solvents used in the reaction, or due to deprotection process, or the reaction will be slow and the side reactions will be faster. Then the side reactions gives the byproducts along with our products too. What are the types of side reactions we can come across in peptide synthesis? Side reaction can occur due to the protonation. Protonation occurs generally in the presence of an acidic environment, or it can also occur due to the abstraction of proton. This generally occurs in the presence of strongly basic conditions, or overactivation can also lead to side reaction. And there are side reaction which is displayed by individual amino acids because of the presence of the functional groups in it, because of the reactivity of this functional group. There are few side reaction which disrupt the peptide bond and deletes the bond which has been formed. This is another set of side reaction which we see. And there are other side reactions which leads to alkylation of the side chain. Let us discuss with the side reactions due to protonation. As we know, protonation leads to racemization. When there is a peptide and during the acidic environment in the presence of H plus, the carbonyl oxygen gets protonated. This acts as an electrophile. In the electrophorescence of electrophile, there is an electromagnetic effect across the carbon oxygen double bond, and the pi electrons moves towards oxygen, which makes oxygen anionic in nature and carbon cationic in nature. Because this anion is electron rich, it combines with the proton and thus the protonation occurs. Once the protonation occurs, the pi electrons are shifted towards the oxygen, which gives rise to the carbocation. Carbocation, as is electron deficient, it pulls the electrons from the adjacent carbon and making this protons attached to the alpha carbon acidic. In the presutable base, or generally to satisfy the positive center, the carbon nitrogen bond breaks and these electrons are utilized to satisfy the positive center and H plus gets removed, giving rise to alkene, and the enolized amino acid is formed. And this occurs because of the acidic environment which we use during the deep protection. By using strong acids like hydrogen bromide or hydrogen fluoride, and this leads to loss of chirality that exists in the peptide which is formed, and thus the further reaction stops. The protonation can also lead to fragmentation of the chain. Here, if I take L-alyl, L-serine, in which it has a carbonyl group. In the presence of the acid, electrons moves towards the oxygen, which attacks on the hydrogen plus and gets protonated, creating a carbocationic center at this junction. In the side chain, the functional group OH which is present, which is electron rich, form bond with this positive center and leads to cyclization, and it has to maintain its valency. That's why carbon nitrogen bond breaks and it disrupt the peptide bond which has been formed and fragmentation has occurred. Here CO bond is formed and here CN bond is broken. This N to O shift occurs when there is an acyl group present in the peptide chain. This is the side reaction which occurs due to O protonation and leads to fragmentation, and thus the disruption of the peptide bond occurs. That's why while using the acidic environment for deprotection, we should optimize the conditions, or we should protect the functional groups present in the side chain. Here the serine has OH group. If we protect this OH, it do not react with this positive center, and thus we can stop the fragmentation. This is how we can overcome. And glycyl glycine, it is having the lone pair of electrons, and when it is attached to the solid support, if this has been protected, is activated as benzyl esters, it gets retracted from the solid support, and when this it gets relieved from the solid support, this carboxybenzyl ester, it has a carbonyl group. There is lone pair of electrons in the nitrogen. It attacks on the carbonyl carbon, and the bond between carbon and hydrogen breaks, and this leads to cyclization to give diketopiperazine. And this removed group will lead to phenol. The benzyl ester generally get premature cleavage of the chain from the insoluble support. And these esters which are getting cleaved by this insoluble support prematurely undergo cyclization to give diketopiperazine. This diketopiperazine can be hydrolyzed and it opens up to give the amide bond, but however it gives the molecule with different stereochemistry which is inactive, which is of no use for us. That's why we have to be taking care about protecting the premature cleavage by the insoluble support by optimizing the reaction conditions. In the next presentation, let us deal with the side reaction due to proton abstraction. Till then, have a nice day.